Yeah, thank you. Yeah, so I've been doing this for 25 years, and very seldom you get to kind of do a side-by-side comparison. Everything is similar conditions, similar flight time, yeah. And as John said, it's a competitor, similar price point, similar weight, top level specification is also very similar. So now we can see how the data actually performs. And I'm very happy, so that means probably HySpex is better. Yeah, so the camera number one is a HySpex VS620. That's our kind of workhorse when it comes to drone cameras. And then there's a core line, also VS camera from a competitor. On the conditions, they're both flown right after each other. New camera from both suppliers, all data flown in one flight. So everything I show now is one flight. Sunny weather, mid-September, Rochester. Both systems have similar price point and both solutions are below 25 kilos. This presentation is taken from my 1 hour talk, so I'll have to speak a bit fast, but I'll reduce that on the slides, so I've taken the most important. One disclaimer is that we were 4 people here, Jeanette, Jeff, and Aga as well. We operated the sensors on behalf of HySpex. While for the competitor, it was a new customer operating it, just been trained. Yeah, and we use a gimbal because we always recommend that when you have a push-button system on an octocopter, while the competitor did not. I will not go through the specification. These are the top-level specification. They are very similar. As John touched upon, here is the calibration row. I will use some, this is our flare mirrors for the drone cameras, supplied by Lapser here. I will use these, I will use these targets for Keystone, I will use these for some apparent SNR. I'll come back to that. And also, I treat the camera plus processing chain as a black box, meaning that I will not look at the raw data of our suppliers or competitor. It's the georeferenced radiance data after it's been processed by each company. So I treat it as a black box. Let's first do a subjective evaluation of the SNR. As there's like, in the visible near infrared, there's 2 problematic areas. It's the beginning of the spectra and the end of the spectral range. So you have a HySpex picture of 410 nanometers on the right and a competitor on the left. Already you can see a lot of striping here. You can also see that the sharpness on the right one is a lot better. 420. It's getting a little bit better on the left there. 430. And 440. For all bands, HySpex has good SNR. Then let's go to the end of the spectra. This is at 900 nanometers. Competitor here, HySpex here. 920, 940, 990. I don't think I need to comment, but okay, let's go to the short wave. Let's go to the end of the spectra from 2000 to 2500 in the extended SWE range. And here there were some problems with the georeferencing of the competitor, so they're lacking some data here. But look away from that. So this is 2400 nanometers, 2420 nanometers. And also you can see, I will come back to that, some striping in the competitor data. 2440, 2460, 2480. There's no data in the competitor camera, and you can see also we are starting to struggle a lot with the signal, and to 500. And then let's look at some stats on the SNR. Since we don't have an integrating sphere here and stable illumination, stable targets, I'm using these big reflectance targets here. I think it's 25 patches of targets put together, or 20. So I'm doing the stats on this whole target for both sensors, and I call it apparent SNR, right? Because there is a non-uniformity in this target that limits actually the max SNR that you will be able to get. And as you will see on the next slide, it's about 50. So basically what the apparent SNR is doing then is evaluating if you have any other noise contribution that limits your SNR to less than 50. So, and also here, to be fair, because the competitor cameras in the visible range, they flew with more bands than us. So to be fair, I scaled their SNR up by the square root of the number, the factor of the difference of band. So that means that if we do binning, we will not benefit from doing binning since the competitor didn't do it. So it's a fair comparison. As you can see, HySpex has stable. The target is the limiting factor of the SNR for the whole visible range, while the competitor has other noise sources that are dominating more. So they have lower SNR for the whole range. For the shortwave range, it's a bit more similar, at least in the beginning. We are at 50, both of us, and then, as you also saw from the subjective evaluation, we are a lot better in the end of the spectral range. Then let's look at the dimensionality of the data. So MNF you can look at eigenvalues. Once you start, the spatial information starts to disappear, means you don't have any more information. This is the visible cubes. This is 16 eigenvalues. 1, 2, 3, 4, going like this. You can see HySpex have the first 16 are okay, while for the competitor, you are starting to struggle after just a few. But there is one good specs on the competitor data. That's the MNF for the shortwave. This is HySpex. This is the competitor. Still, it's quite similar, good eigenvalues, but you see a structure into eigenvalues in HySpex. The HySpex data is a lot sharper. Both competitors are doing resampling on the smile. So this is actually residual resampling errors. And since ours is sharper than the competitor, our aliasing is stronger. So I'll give the point to the competitor on this one spec. Yeah. Then let's look at the sharpness. So these are the mirrors on black backgrounds. Many different targets along the calibration row. So let's start with the visible. That's this one. HySpex here, competitor there. So these are evenly distributed band from 410 to 1000. So through the whole range. So I'm glad that this projector is good. So you can see that in the HySpex data, you see the point sources in all bands, and they're sharp. And remember, this was also georeferenced, and it's georeferenced with nearest neighbor resampling. So geometry can be a little bit coarse. And then we go to the competitor. Yeah, you can see some point sources here, some weak here, and then it's not so simple to see. For the shortwave infrared, again, through the whole range from 950 to 25, you can see in all bands the point sources in HySpex. And yeah, you can see, but it's very hard. But also here, I would say, it's not only the sharpness of the camera here, but also the fact that they don't use a gimbal comes into account, right? Their loss. And then this is one of the most important specifications when it comes to imaging spectrometers. That's the spatial misregistration. So I would typically use the point sources to do this, but since I couldn't see them in the competitor data very well, I have to use edges on black and white surfaces. So the keystone of spatial misregistration is the misalignment of spatial misalignment of bands of different bands. And already here in this false color RGB, you see coloring effects on the competitor data, meaning they have big misalignments, while these edges here are gray, meaning that we have less. But if you look at the actual edge position, so the edge position doesn't only take into account keystone, right? It also takes into account SPSF shape changes, because that can also happen. So this is a combination of SPSF changes in the shape and the center of gravity, the keystone. So HySpex here for the visible range, shortwave range, competitor here. It's the same, to sum it up. Yeah, less than 20% of pixel in the visible range. I was nice with the competitor. I said 1 pixel, it's more, but yeah, maybe more than 1 pixel. And for the keystone in the sphere, 30% of a pixel, while 50 in the competitor data. And just to say how important this is, if you have a airborne or UV camera with a PSF of 1.5 pixels, and you have 30% keystone, you will have a 7% error in all spectra due to keystone in that image, in average. And that's based on an article we made some years ago, and based on 100 gigabytes of airborne data to evaluate this. So this is a really important specification for the spectral fidelity of your camera. And then striping, as I showed earlier, you have stripes in the competitor data. You will never find stripes in a UV camera from HySpex because we have a patented design in the optics. So stripes in push-broom cameras are a big problem in general. You want to get the slit as sharp as possible because you want a sharp imaging system. So we have a patent where we defocus the slit in a cross track before you cut it out, and you focus it back right after. So you get insensitive to small movement, which you will have in almost every push-broom system. So we don't get these stripes that you see here. And then let's look at the spectra relative to the ground data. This is a single pixel spectra. The red one is the competitor, and the blue is us. So of course you already see some noise issues here, but to be able to compare, I average 5 by 5 pixels on the targets. Now I also added the ASD ground measurements, so the red one, you can see it's quite nice relative to the HySpex data. And also I want to just show that if you also look at spectral sharpness, for example, you have HySpex and ASD here, while the competitor is a lot less spectrally sharp. Then let's look at the shift. For the visible range, I used the 760 line to evaluate the shift. So I then resampled ASD to center variant of each camera. So on the left side, you see HySpex, 0.18 nanometer. So my conclusion is that ASD, of course, is 0.18 nanometer wrong, and that we are right. But yeah. But anyway, on the right side, you have the competitor with almost 3 nanometers offset between the ASD and their 760 line. And then for the shortwave, I used the 2000 features. Again, minus 0.18 here for HySpex, and 3 times or more than 3 times more on the competitor data, 0.71. Then let's look at SMILE. So SMILE is misalignment of the spectral features across the field of view. So I used 4 points across the field of view and looked at how the shift of this feature changed with position. So for the shortwave, we are about 0.3 nanometers SMILE. The competitor more than 3 times more. 1 nanometer for the visible range. Yeah, we are at 0.1. The competitor is 5 times worse with 0.5. Then both of us, we are making core-line system. So it's very important that veneer and sphere are core-line in one cube. So this is HySpex data in NV, just showing the cubes separately, and just subjectively here first, showing that there's very little different in the position of the pixel in this shortwave and the visible cube. If you got the competitor data, they have the data separately. So when I step around, I just need to look at the position. And this is more than 5 pixels off between veneer and sphere cubes, which basically means that you can't use it as one cube, right? Because you have a 5 pixel misregistration between veneer and sphere. So basically you have a keystone in the full cube of 500%. But yeah, but to go a bit closer into the keystone, the misregistration in the cubes in HySpex, so I didn't do that for the competitor then. I looked at the keystone for the whole spectral range, and you will expect a dip here, which will then be the misregistration between the cube. So I can say that we have about like 10% of a pixel misregistration between the near answer. And this is, of course, taken several places in the field to make sure. So to sum up, I haven't showed all this today. I don't think I've showed the stray light because I didn't have time. Yeah, green means better. So, and there are significant changes, differences. It's not just small differences. And as I said, on the MNF here, I gave the point to the competitor. And yeah, for the operational part, I just want also to mention that when you buy a UV system, you also want to operate it as efficient as possible. With our solution, you can connect to it. You can see if you are over or underexposed during the flight, change settings. That is not possible with the competitor system. You need to set the integration time before you fly, and then hope that you're not overexposed. I think you have some target or something to put it during the flight. We use gimbal, they don't. I think that's a big problem for them. Yeah, we also have a mechanical shutter to do the dark current. And that's a big problem in the competitor data, because you actually, when you turn on an extended sphere camera, it will drift the dark current, especially in the beginning. So when you then take a dark current before you fly and one after, that is not stable if you do a linear interpolation between the flight. So we cut up the flight lines, and between each of them, we take a new dark currents to get the best offset compensation. Yeah, and of course we supplied data very fast, even during ROXC, and yeah, it took a bit longer for the competitor.
Okay, thank you.
Questions?
Is there one quick question?
It's impressive results for the HySpecs, very impressive. How much of the competitors' challenges were due to the lack of gimbal? And are you thinking of going head-to-head with gimbals again in round 2?
I really hope with all the keystone smile, that doesn't have nothing to do with gimbal, right?
Yeah.
It's only on the sharpness and the PSFs, the PSF that we evaluated, that could be better with a gimbal for them. So, yeah. More?
I think it's time to move on. Thank you, Trond.